Hello. Hey.
All right. X squared minus 17x. It's a video.
Yeah, it is. Boom! It's a video. Or I meant like not of the class. No, but it's a video still. Wait, does that mean if we get in front of the
Yeah, go. Go do a dance or something. Do some Gundam style or something. Do a dance. All right.
Jacob, you should go.
X squared. Oh, somebody did.
Joe's here.
I wanted the child did it earlier. 6x squared minus 17x plus 12. 3x minus 1. First of all, what's the y-intercept? Negative 12. Right? Plug 0 in for x. 12 divided by negative 1. Boom.
Do it, Karen.
X-intercepts. So at the top equal to 0, so 6x squared minus 17x plus 12 equals 0. Is that even factorable? Does anything multiply to 72 and add up to negative 17? 6 times 12. 6 times 12. Does anything multiply to 72 and add up to negative 17? Yeah, negative 8, negative 9. So this becomes 2x minus 3, 3x minus 4. Because here's your negative 8, negative 8x, here's your negative 9, and that makes you negative 17. It's positive 12. Okay? Make sense? So our two potential x-intercepts are at 3/2 and at 4/3. Double check real quick. Do either of those numbers also make the bottom of this fraction 0? No. No. So those are definitely x-intercepts. And those x-intercepts are really close together. Right? 1.5 and 1.3. So a y-intercept, two x-intercepts, that's beautiful. Where is this graph discontinuous? At 1/3. Does 1/3 happen to make the top 0? No. So that is definitely a vertical asymptote. Great. Let's analyze that vertical asymptote real quick. This function, f of x, is, what does it factor down to? 2x minus 3, 3x minus 4, all over 3x minus 1. So what is the limit as x approaches 1/3 from the left of this function? Well, let's think about it. A number slightly smaller than 1/3. You're going to get a what type of number for this factor? This will be negative. How about 3x minus 4? Also going to be negative. But what's 3x minus 1 going to be? Also negative.
Well, the way you phrase that question.
You can't trust the way I phrase things. Okay? Actually, true story. 1987. I was 5 years old. Epic snowball fight. Took a frozen snowball to the temple. And ever since then, I have not been able to phrase things in a proper tone of voice that implies what the answer is. So I get that all the time. Like, I phrase something, and people are like, no, it's positive. I actually didn't mean to phrase it that way. I can hear the way I phrased it.
Is this true?
Yeah, I just said it's a true story. I mean, that totally is realistically believable with the anatomy and how the brain works.
I believe.
Man. So that is a negative. So that's going to negative infinity on the left.
I don't want to drop those drops. Most definitely.
Okay. Now, as x approaches 1/3 from the right, that factor is going to be negative. That factor is going to be negative. And that factor is going to be
negative.
Positive.
My first name.
Right? Or a number slightly larger than 1/3. Those are still going to be negative, but when you take a number larger than 1/3 multiplied by 3, you get a number larger than 1. So on the right side of 1/3, it is in fact going to positive infinity. Right? Right. Okay. So there's our analysis of the vertical asymptote, and that analysis is essential to graph this function, right? You need to know which side, you know, maybe it's up on both sides, down on both, left, down on the left, down on the right. Yeah, I'm going to want to see, when you get a vertical asymptote, I want to see you describe the behavior around the vertical asymptote using some sort of limity notation. And then finally, what is the end behavior for this function? What do you think? Does it have a horizontal asymptote? No. If I plug in a really, really large number for x, what's this function going to output? A really, really large number. And if I plug in an even bigger number for x, it's going to output an even bigger number. Okay? This is not a horizontal asymptote. In fact, what do you get when you divide the dominant terms? 2x. So this thing is going to have the same end behavior, same EB, as a polynomial with a positive leading coefficient, positive 2, and odd degree, because the degree was 1. It's going to have the exact same end behavior as a polynomial with positive leading coefficient and odd degree. Because when you divide the dominant terms, that's what you get, positive leading coefficient, odd degree. So what does that end behavior look like? That is f of x approaching positive infinity as x approaches positive infinity. That is f of x approaches negative infinity as x approaches negative infinity. So that's up to the right, down to the left. Right? But I want to do even better than that. Figuring out the end behavior, yeah, that's easy. Everybody should be able to do that. It's a piece of cake. But there's actually some polynomial out there that if I take the graph of this rational function and I zoom out forever and ever and ever, so this is what we looked at last Thursday, or last Wednesday actually, the global scale, what does this graph look like if I were to zoom out forever and ever and ever and ever and ever? It's going to look like some line. I want the equation of that line. What is the equation of the line that this function is trying to look like if we were to zoom out forever and ever and ever? We just want to divide this thing out. So let's take 6x squared minus 17x plus 12 divided by 3x minus 1. Now we are dividing by a linear, so can I actually do this with a synthetic division? No. Not the way it looks right now, no. Not when there's a 3 in front of the x. Could I modify these polynomials in a creative way that would allow me to do synthetic? So you have a choice. Do you just suck it up and do the long division? Or do you modify this so that you can do synthetic division? Not only do you have to know how to modify them, but you're going to end up creating synthetic division with some pretty gross fractions. I think this is long division. Okay. So what do you multiply 3x by to get 6x squared? 2x. So there's our 6x squared and a minus 2x. Real quick, what's negative 17 minus negative 2? Negative 15. Good. What do you multiply 3x by to get negative 15x? Negative 5. There's a negative 15x plus 5, and that gives me a remainder of 7. So if I add 7 over the divisor, that is called the divisor, right? Does everybody agree what I just boxed in, 2x minus 5 plus 7 over 3x minus 1, is actually the same exact function as what we started with, 6x squared minus 17x plus 12 over 3x minus 1. They are exactly the same thing. Okay, they are. Those are the same thing, just different versions, different ways of writing them, right? Remember how our simple rational functions had 2 different ways they can look? It's the same idea here. Now let's focus at this, okay? As x gets really, really, really huge, what does this remainder fraction essentially become? 0. So let's pretend it actually is 0. That means as x gets huge, this function looks more and more like, we're going to call this the global scale, y equals 2x minus 5. That is the line that this function is trying to look like. And because it is a line, you will often hear people call this the slant asymptote or oblique asymptote. Okay? So now I feel pretty confident we can graph this thing really, really accurately. Okay, let's get a nice grid. I don't need to be that small. Some axes. Maybe I do want it that small. Oh, not my axes messed up. Okay, so where was the y-intercept for this graph? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The y-intercepts were at 3 halves, which is right here. X-intercepts, what did I say? Oops. And also at 4/3, which is just barely to the left of that one. Right? So you have 2 x-intercepts really close together. What else did we know about this graph? There's a vertical asymptote at what? At 1/3. Oh my goodness. Interesting. Okay? And I also analyzed so that I know on the right side of the vertical asymptote the function is going up to infinity, right? And on the left side it's going down. Okay? And then we discovered a slant asymptote with the equation 2x minus 5. So if I go down to -5, put a mark, and then slope up to over 1, right? Yeah, I'm using the highlighter because it's a asymptote. I don't know why I always prefer highlighters for asymptotes. I don't know why. Okay? And so that's what we have. Slant asymptote, 2x minus 5. Whoa. That was bad. Try that again. Okay? Make sense? I need you better go now if you're going to go early. Okay. So then I feel pretty confident we can draw this thing, follow along that slant asymptote, and then curve through that y-intercept. Vertical asymptote. Cross through those x-intercepts. There is going to be a little dip there. The very bottom of that dip is slightly below the x-axis, right? So it does go negative a little bit, but that's pretty much it. And if you zoom out forever, if you zoom out so far you don't see that vertical asymptote at all, you're going to see a graph that just looks like the line 2x minus 5.
Is it important that we graph the
No, the minimum and the actual heights of the minimums and maximums are going to be incredibly inaccurate in most cases. Good. We're trying to do this by hand. You're not going to have your graphing calculator for Friday's quiz. So we have no way of finding out where those maximums and minimums are. Not until calculus next year. And even for a function like this, it's gross. That's gross math. Yeah, you want to see some good? Has anybody installed GeoGebra at home yet? Nobody? Oh, that's sad. You think? So, what was this? 6x squared minus 17x plus 4 plus 12 divided by 3x plus 1 minus 1. And there it is. I'd say that looks pretty darn similar to what we drew by hand, doesn't it? Well, we're zoomed in pretty far. We zoomed. So there. Okay, now let's graph on top of this. Let's zoom in a little bit so we can actually see it. Let's actually graph that 2x minus 5 line. So y equals 2x minus 5. Okay, so that is the line that is acting as our slant asymptote, right? That's perfect. We could also graph the line x equals 1/3. See our vertical asymptote in there as well. Pretty cool? Pretty cool. So you wanted to zoom in to actually see if it does, in fact, dip below the x-axis? Oh, yeah. Right? Pretty cool. Okay. So feel pretty good about these? Let's do another. Now, again, no graphing calculator. Yes. So what's the y-intercept?
-5.
Negative 15 divided by 3 is negative 5. Very nice. X-intercept, we take the top, x cubed. Bye, Austin. Bye, Allie.
He's an officer.
Whatever, Mad. Mad. Maddie. Madison. Okay. So x cubed plus 3x squared minus 13x minus 15. I would love if that was factorable by grouping, but it's not. And we don't have a graphing calculator, so we can't guess. We actually have to guess. However, there's not many options, and if you look at the numbers, see how the first coefficients are really small and the second ones are both negative and they're bigger? An obvious one's not going to work, right? So I'm probably going to try 3, and I don't think 15 is going to work either. Or 5? Let's try 3. So we go with the 1, 3 and 3 is 6, 18 and negative 13 is 5, and 15 and negative 15 is in fact 0. That's great. And so then this is x squared plus 6x plus 5. That is nicely factorable to x plus 5x plus 1. So we have 3 potential x-intercepts, positive 3, negative 5, and negative 1. Do any of those 3 numbers also make the bottom equal 0? Right. So far today, everybody says 3. Yeah? Second period. Today, yeah. Yeah.
How many people were in there?
Like 6 or 7. There's only 18 in that class actually. There's only 18 total students. So like maybe 6 or 7 were juniors, 1 was a senior. Okay. So all of these are x-intercepts. 3, 0, negative 5, 0, negative 1, 0. Boom. Those are nice numbers. Nice y-intercept. 3 definite x-intercepts. That's great. Where is this graph discontinuous? At negative 3. Does that number also make the top 0? No. So a definite vertical asymptote. Set the bottom equal to 0. Shall we analyze that vertical asymptote? Yes. The top factors down to x minus 3x plus 5x plus 1, correct? The bottom is x plus 3. So let's analyze the limit as I approach negative 3 from the left of this function. Well, let's go factor by factor. So I'm a number slightly to the left of negative 3. The first factor, x minus 3, will be negative. X plus 5 will be positive. A number close to negative 3 plus 1 will be negative. And the factor that's the most difficult to predict is x plus 3. We're a number close to negative 3, but we're to the left of it. So what do you get when you add 3 to that? A negative. To the left of negative 3. A number smaller than negative 3, like negative 3.1.
Oh, okay.
Right? A number smaller than negative 3, like negative 3.1. Right. So that turns out to be approaching negative infinity to the left. What? If you see an odd number of negatives, it's a negative. So how about as you approach from the right? Well, those top factors aren't going to change. You're still a number close to negative 3. It's only the bottom one that might change. If you're a number slightly larger than negative 3, that is going to create a positive when you add 3 to it, like negative 2.9. So on the right side, it is going to positive infinity. Great. I know that this function, when I plug a number really, really close to negative 3 in, that function is going to output something either close to infinity or close to negative infinity. The number's really, really far away from the origin. It depends on what side of 1/3 you're on, negative 1/3. As you approach negative 1/3 from the left, it's going down. And what I do is I look factor by factor just to determine if it's positive or negative. Ultimately, even with a cheapy-deepy on Friday's quiz, a regular calculator, you could plug in like negative 2.99 and see what your calculator outputs. If it outputs positive 1 billion, that's positive infinity. If it outputs negative 3,000, that's negative infinity. How those limits are written? Is that good? You literally type 6 times negative 2.9. Oh, actually, it's one. No, yeah, it's negative 2.9 to the third. Well, I mean, it's not quick, but you just gotta type it out. Okay, and then finally, what is the end behavior for this graph? Well, it's not a horizontal asymptote, right? So what is the end behavior going to be similar to? A polynomial whose leading coefficient is positive, 1, and whose degree is even. So that means f of x is going to approach positive infinity as x approaches infinity. F of x is still going to be approaching positive infinity even on the left side, which is as x approaches negative infinity. Okay, up on both sides, just like a parabola. But that's not good enough. I want to know, what is the global scale? If I zoom out on this thing forever, not just what it will look like, the actual equation of what it will look like. So how do we find the equation of we divide. Now this one we could use synthetic, couldn't we? Very nice. So we go 1. Yeah, and you're right, we haven't done it. Like, this division by 3 would actually be the factor x minus 3. Since it's x plus 3 we're dividing by, you put a negative 3 in front. Good. So 1, negative 3, 0, 0, negative 13, positive 39, and then what is negative 15 and 39? 24. So when you divide, you get x squared minus 13 plus 24 over x plus 3. But again, what happens to that fraction as your inputs get gigantic? It becomes 0. So the global scale is the parabola y equals x squared minus 13. It's just your typical parent parabola shifted down 13. That's it. If you wanted to be fancy, could you call that parabola a parabolic asymptote? I mean, it acts the same, right? Now, when you hear the word asymptote, you should assume it's a line. But really, it's the same concept. It's the same idea. The more extreme to the edges we get, the closer that rational function gets to actually being the parabola. Okay? And that's an easy parabola to graph, isn't it? I was pretty generous creating a parabola that did not have a middle term. It's already in vertex form, right? So we can easily graph this parabola, graph the vertical asymptote, graph the intercept, use all of that to draw a really darn good sketch. Now I'm going to, hopefully you guys still have it written on your paper so you can remind me as we go. So it's not visible to me anymore. All the information. So when I ask you for something, make sure you tell me. All right, what's the y-intercept? -5. What are the x-intercepts? 3, -5, -1. What was the vertical asymptote? -3. X equals -3. And on the left, am I going up or down on the left side? Up?
Down.
Oh, is it down? So it's down on the left, up on the right? Okay. And then our global scale was a parabola shifted down 13. Uh-oh. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And has that parabola been stretched in any way? No, so I can go right 1, up 1. I could go right 2, up 4. I could go right 3, up 9. I could. You just wanted to be all crazy. We could go up 16, which is actually going to be here, right? I think that's pretty good. That's enough. Well, that was not very good. Yeah, I know. It looks more like a degree 4, doesn't it? So we get this nice parabolic asymptote there, right? Okay. So what does this mean? Oh, man. This is kind of weird. So is it going to be like... Alright? And then... Is it going to be like that? I'm definitely going to want to grab this one in GeoGebra because that was kind of strange. Does that make sense?
We did something like that on GeoGebra and it had like an insane amount of lines.
Yeah, I gave it a bunch of, the one I created a week ago,
Yeah.
I gave it a whole bunch of vertical asymptotes. Okay, so this was, help me out, x cubed,
3x squared.
3x squared. Yeah, that's pretty much what we got. Right, if you just look at what we graphed in blue. Oh, that's not bad. It's pretty good. Yeah. So if we zoom out. I mean, yeah, it's a parabola. Yeah, let's zoom back in. I actually want to graph that parabola. What was it, x squared minus 13? So if we graph here, y equals x squared minus 13, look at that. Yeah, in the middle of the graph, they're not very close to each other. But on the edges, look at it. The farther you go to the left, the closer and closer our graph gets to that parabola. Same thing on the right side. Okay? Make sense? Okay. That's all I got for you.